Hi there, this is Thermophysics Lesson 3, and this one is specific latent heat. So the starter question. A couple of things that I want to remind you of in case you haven't got them written down is the specific heat capacity of water, which is 4,200 joules per kilogram per Kelvin, or per degree, same thing. Same thing by incremental change. A 1 degree Celsius change is the same as a 1 Kelvin change. And the specific heat capacity of copper, which is 385 joules per kilogram per Kelvin. And then the equation is mc theta. Energy is in joules, mass in kilograms, specific heat capacity above joules per kilogram per Kelvin. Change in temperature is obviously degrees Celsius or Kelvin. So you want to make sure you've got that. Then I want you to pause and have a go at this question. Calculate the heat energy required to raise the temperature of a copper can, mass 50 grams, containing 200 centimeter cubed of water from 20 degrees to 100 degrees. So another thing that we need to know, 200 centimeters cubed. So 1 litre of water, you might already know this, you should know this really, 1 litre of water is 1,000 millilitres. And 1,000 centimeter cubed. So essentially 1 milliliter is equal to 1,000 is equal to 1 centimeter cubed. They're the same thing. And mass wise, a litre of water has a mass of 1 kilogram. So a milliliter is a gram. So let's do the question. So let's do mc theta for the copper. So the mass, 50 grams, so 0.05 kilos, times 385 for the specific heat capacity, multiplied by change in temperature of 80. So that gives us, for copper, 1,540 joules. Then let's do the same for the water. So the mass is 0.2 kilos, 200 centimeter cube, 200 milliliters, 0.2 kilograms, multiplied by specific heat capacity 4,200, multiplied by 80 for the change in temperature, gives an energy of 67,200 joules. And then we simply add these together to give us 68,740 joules of energy. Okay, let's move on. So another starter question. I need to pause and have a go at this one. A continuous stream of water falls to a vertical distance of 150 meters. Assume no thermal energy is transferred to the surroundings. The specific heat capacity of water is 4,200 joules per kilogram per Kelvin. What is the temperature difference of the water between the top and bottom of the waterfall? So it's pretty straightforward. Because we've got no heat being transferred to the surroundings, we can assume that the loss of gravitational potential energy is equal to the gain in thermal energy. So the loss of gravitational energy will be mgh, and that will be equal to the gain in thermal energy, which will be mc theta. So the masses cancel. So to get the temperature change, theta, we simply do gh over c. Then we just need to put our numbers in. So g is 9.81. The height is the 150 meter fall, divided by specific heat capacity, 4,200. So the change in temperature is equal to 0.35 Kelvin, or you could say 0.35 degrees Celsius. Either or. Hopefully you managed to figure that one out. Let's move on. So just some information, some keywords. So most of these we should already know. So ice obviously melts to a liquid, to water, and then evaporates into a vapor. And then the opposite from vapor to liquid is condensation. And then from liquid to ice is freezing. We've got a couple more that you may not be aware of. We've got solid straight into a gas, which is a process called sublimation at the top. And then at the bottom, we've got vapor turning straight into a solid, which is called deposition. And then the top two lines, heat energy taken from the environment, and the bottom one, heat energy released to the environment. So if you want to pause and take note of any keywords that you may need, please feel free to do so. And I'm going to move on. Specific latent heat. So specific latent heat of a substance is the energy required to change the state of unit mass, or 1 kilogram, of the substance without a change of temperature. And in a moment we'll talk about the two different types of specific latent heat. The latent heat of vaporization, or the two main ones should I say, the latent heat of vaporization and the latent heat of fusion. First of all, let's get this equation down. So delta Q equals ml. Q is energy measured in joules. M is mass measured in kilograms. L is the specific latent heat in joules per kilogram. And you can also write this equation, as I probably do most of the time, E equals ml. And normally, like I said, we'll talk about this in a second, L would be LV for latent heat of vaporization, or LF for latent heat of fusion. And I'm going to talk about these in a moment. But if you want to get the information down, the equation and the units, and then I'll move on. So here's some examples of specific latent heat. So as you can see, the top one, ice to water. The state change is solid to liquid. And when you go from a solid to a liquid, or from a liquid to a solid, that's called the specific latent heat of fusion. And the example of ice into water or water into ice, the specific latent heat value is 336,000 joules per kilogram. So to convert 1 kilogram of water into ice, or 1 kilogram of ice into water, would require 336,000 joules of energy. So the next example, water to steam. So that would be a liquid to a gas. That's called the specific latent heat of vaporization. So water to steam or steam to water is latent heat of vaporization. And as you can see, in terms of energy, much more energy intensive when compared to the specific latent heat of fusion. So we've got 2.25 million joules per kilogram. So to convert 1 kilogram of water into steam, or 1 kilogram of steam into water, requires 2,250,000 joules. So it's much more energy intensive than ice to water or water to ice. Then we've got some more examples that you can look at if you want to pause and have a look. And then we'll move on. So the aim of that is to establish the difference, give you some ideas of the numbers, and then establish a difference between, what fusion and vaporization in terms of latent heat are, and the fact that vaporization is more energy intensive than fusion. So to complete this, so let's pause and write your answers down. Be careful of the units. We've got milligrams, micrograms, and mega for megajoules, etc. So be careful of those. And then I'll give the answers, and we'll see if you get them right or wrong. Okay, so the first one, 1.344 megajoules. Next one, 67,200 or 67.2 kilojoules. Next one, 4 kilograms. Next one, careful with the units with the milligrams, 1,350 joules. The next one, 4,560 joules. And the last one, you have to be really careful with the micrograms. So that would be 40,000. No, if it was grams, it'd be 40,000 times 10 to the minus 3. And then with the micro, it's another minus 6. So it'd be 40,000 times 10 to the minus 9. And that gives an energy of 22.8 joules. Okay, let's move on. Hopefully that went okay. So just a slight recap, mainly from GCSE. So the internal energy of a system is equal to the sum of the potential energies plus the sum of the kinetic energies. And a change in potential energy is a change in state. So in terms of equations, the sum of the potential energies is normally mass times the latent heat of fusion or vaporization. And kinetic energy involves the movement of the atoms or molecules of the substance itself. So if they move faster as they gain energy, then the temperature would increase. So the equation that satisfies the kinetic energy one is the MC theta. So again, internal energy is the potential energies plus the kinetic energies. And there's a graph on the next page, and I'm going to describe the graph to you and explain some things before we finish. So let's move on. So here's a graph. So this is maybe heating ice. So obviously this is 0 degrees. So what's happening then? Well, in this first region, this region here, we've got an ice being heated up. So this is a change in temperature. And then this one is a phase change from ice to liquid. And this is a liquid increasing in temperature to its boiling point. And this region of the graph is liquid into a gas, so a phase change. And then this final bit is warming of the gas. So I'm going to link this to the equations. So this first region, the equations, because it's a change in temperature, this region will be MC theta. This flat region is a phase change. So that will be mass times the latent heat of fusion. The next part, change in temperature. So again, this is described by MC theta. Apologies, I knocked them off then by accident. I've drawn them back in. So this bit is a phase change. So that is the mass times the latent heat of vaporization this time. And then this bit with the change in temperature, yet again, is MC theta. So as you can see, there's a visible difference between the length of time it takes for the MLF compared to the MLV. So that because the latent heat of fusion, the value is less than the latent heat of vaporization. The latent heat of fusion is 336,000 for water. And for a water turning into steam, the latent heat of vaporization is 2.25 megajoules per kilogram. So the length of time would be, it actually would be much more exaggerated if it was a to-scale graph. So in terms of energy increasing, increase in kinetic energy, increase in potential energy, increase in kinetic energy again, increase in potential energy, increase in kinetic energy. Now at all times, as you're heating this substance, heating the ice, the internal energy will obviously be increased, because internal energy is simply the sum of the potential energies plus the sum of the kinetic energies. But each region of the graph is either kinetic energy or potential energy. Now for this reason that we just talked about, a typical exam question is what can replace temperature on the y-axis? And the answer is kinetic energy. Kinetic energy is synonymous with temperature when it comes to heating substances. So I hope that helped. Next session we're going to look at a lot of exam style problems. There's some very tricky ones in the next lesson, so I advise that you watch it. So thanks for watching, and I'll speak to you soon.